The edge of the observable universe is 46 billion light-years away, in every direction. Perfect sphere, perfect symmetry. That is what the models predict. But when astronomers mapped the cosmic microwave background, the most precise measurement of that edge we have ever made, they found something impossible. One side is different from the other. Not slightly different, measurably different. And the asymmetry points in a direction. The same direction across multiple independent measurements. Galaxy clusters are drifting, not randomly, all moving toward the same region of space at 600 kilometers per second, as if something beyond the edge is pulling them. For 70 years, cosmology has been built on one principle. The universe is isotropic, the same in all directions, no preferred orientation, no special axis. It is the foundation of the Big Bang model. But 3 different space telescopes have now confirmed the same thing. The edge has geometry, the edge has structure. And in 2005, when frustrated cosmologists saw the data, they gave it a name, the axis of evil. If you have been following this channel, you know I track precision anomalies, objects that are too perfect, or not perfect enough. 3I Atlas, the moon's tidal lock. Things that break our models. But while we were analysing comets and craters, cosmologists were quietly documenting the biggest anomaly of all. The universe itself. The observable universe is not symmetric. And if it is not symmetric, then something we believe about the Big Bang is wrong. Make sure you are subscribed, because today we're going to look at the data. Not philosophy, not speculation. Actual measurements from the Wilkinson Microwave Anisotropy Probe, the Planck satellite, and ground-based observatories. And what they reveal is disturbing. The edge of the universe has a direction, and we need to figure out why. Let's start with what the edge actually is. When we say the observable universe, we're talking about a sphere centered on Earth, a sphere 93 billion light-years across. That is the distance light has had time to travel since the Big Bang, accounting for the expansion of space. Everything inside that sphere we can see, everything outside we cannot. Not because there is nothing there, but because light from those regions has not reached us yet. The edge is not a wall, it is a horizon. And just like the horizon on Earth, it moves as you move. But here is the thing. That horizon should look the same in every direction. If you're standing in the middle of a flat desert, the horizon is the same distance away no matter which way you turn. Same principle. The universe expanded from the Big Bang. It expanded uniformly. We are not in a special location. So when we look out to the edge, we should see the same thing in every direction. Same density of galaxies. Same temperature, same structure. This is called the cosmological principle. It is not just a guess. It is a requirement. If the universe is not isotropic, then our models of how it formed do not work, and for decades it seemed true. Early maps of the cosmic microwave background showed a nearly perfect uniformity. The CMB is the afterglow of the Big Bang. Light that has been travelling for 13.8 billion years, it fills the entire sky. And when we measure its temperature, it is almost exactly the same everywhere. 2.725 Kelvin. Everywhere. To within a few millionths of a degree. That uniformity was proof. The Big Bang happened everywhere at once. The universe expanded uniformly. Case closed. Except it was not closed. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe. Its job was to map the CMB in higher resolution than ever before, find the tiny fluctuations, the seeds of galaxies, and it did. But it also found something else, something that should not be there, a pattern, a large-scale alignment in the CMB, features that line up with each other across opposite sides of the sky, features that should be random, but they are not random. They are aligned with the plane of the solar system. Let me explain what that means. The cosmic microwave background is 13.8 billion light-years away. It formed 380,000 years after the Big Bang. Long before the solar system existed, long before the Milky Way existed. There is no reason, no physical mechanism for structures in the CMB to align with the ecliptic plane of our solar system. None. And yet they do. The quadrupole moment of the CMB, the large-scale hot and cold regions, line up with the plane of Earth's orbit around the Sun, as if the universe knows where we are, as if we are in a special location. In 2005, two cosmologists, Kate Land and João Magejo, published a paper analysing this alignment. They could not explain it. No model predicted it. So they called it what it was, an anomaly. And because it seemed to violate the cosmological principle, the foundation of modern cosmology, they gave it a name, the axis of evil, not because it is sinister, but because it should not exist. And yet, there it is, in the data, confirmed by multiple independent measurements. Now, you might be thinking, okay, alignment. Strange. But maybe it is coincidence. Maybe we just happen to see a pattern. After all, humans are good at seeing patterns even when they are random. Fair point. So let's talk about probability. The quadrupole alignment has been analysed statistically. The odds of it occurring by random chance are less than 1%, less than 1 in 100. That is not proof. But it is enough to raise questions, and the axis of evil is not the only anomaly. In 2004, astronomers analysing WMAP data found something else. A cold spot. A region of the CMB that is significantly colder than the surrounding area. About 70 microkelvins colder. That does not sound like much. But in the CMB, where temperature variations are measured in millionths of a degree, 70 microkelvins is huge. The cold spot is about 1.8 billion light-years across. It sits in the constellation Eridanus, and it should not be there. Here is why. The CMB has fluctuations, hot spots and cold spots. That is normal. Those fluctuations are the seeds of galaxies, regions where matter was slightly more dense. Gravity pulled on those regions. They collapsed. Stars formed. Galaxies formed. We understand this process. We have mapped millions of these fluctuations, and they follow a pattern, a statistical distribution. Most fluctuations are small, a few are medium, very few are large. It is a bell curve, and the cold spot is an outlier, way out on the tail of the distribution. The probability of a cold spot that large existing by random chance is about 1 in 50,000. 1 in 50,000. So cosmologists looked for an explanation, and they found one. Sort of. In 2015, a team of astronomers discovered a supervoid, a massive region of space with fewer galaxies than average. It sits roughly in the direction of the cold spot, and the theory is that light passing through the supervoid loses energy. It gets redshifted, and redshifted light appears colder. So the cold spot might just be the shadow of this supervoid. Problem solved. Except it is not solved, because when astronomers measured the supervoid, they found it is not large enough, not empty enough. To create a cold spot that size, you would need a void at least twice as large. The supervoid explains maybe half of the temperature drop. The other half? Unknown. And there is another problem. The cold spot is not just cold, it is also aligned with the axis of evil. The large-scale structures in the CMB, the quadrupole and the cold spot point in similar directions, toward the constellation Eridanus, toward the same region of space. That is not supposed to happen. These are independent features. They should be random, but they are not. They are aligned. Which brings us to the third anomaly, and this one is the strangest. In 2008, a team of astronomers led by Alexander Kashlinsky was studying the motion of galaxy clusters. Not individual galaxies, clusters. Groups of hundreds or thousands of galaxies bound together by gravity. These clusters should be moving randomly, some toward us, some away, some left, some right. Averaged out, the motion should cancel. That is what isotropy predicts. But Kashlinsky found something else. The clusters are not moving randomly, they're drifting, all of them, in the same direction, toward a region of sky in the constellations Centaurus and Hydra, at 600 kilometers per second. This is called dark flow, and it is a problem, because there is nothing in that direction to pull them. No massive supercluster, no giant attractor, nothing visible. Which means either there is something beyond the edge of the observable universe pulling on them, or the universe is not isotropic. Either option breaks the standard model. Kashlinsky's team analysed over 1,400 galaxy clusters using data from the Wilkinson Microwave Anisotropy Probe. They used a technique called the kinematic Sunyaev-Zeldovich effect. When light from the CMB passes through a hot galaxy cluster, it gets a tiny energy boost, and if the cluster is moving, the boost is directional. By measuring that boost across hundreds of clusters, they could map the motion, and the motion is not random, it is coherent, all moving in the same direction. Now, dark flow is controversial. In 2013, the European Space Agency's Planck satellite released its own CMB map. It was more detailed than WMAP, and the Planck team said they did not see dark flow, they saw no coherent motion. Kashlinsky's team looked at the Planck data, and they said they do see it. It is still there, just harder to detect because of the way Planck processed the data. So the debate continues. But here is the thing. Even if dark flow is disputed, the fact that it was detected at all is significant, because it fits the pattern. The axis of evil points toward Eridanus. The cold spot sits in Eridanus. And dark flow moves galaxy clusters towards Centaurus and Hydra, which are adjacent to Eridanus. 3 independent anomalies, all pointing in roughly the same direction. So, what does this mean? Let's go through the options. Option 1. It is all a coincidence. The axis of evil, the cold spot, and dark flow are unrelated statistical flukes. Possible, but unlikely. When you have 3 independent measurements all showing us symmetry in the same direction, coincidence becomes harder to believe. Option 2. There is something beyond the observable universe, something massive, pulling on galaxy clusters, influencing the structure of the CMB. This is the pre-inflation hypothesis. Before cosmic inflation, the rapid expansion in the first fraction of a second after the Big Bang, the universe was smaller. Matter was closer together. If there was a massive concentration of matter in one region, it could have exerted a gravitational pull. Then inflation happened. Space expanded faster than light. That massive structure got pushed beyond our observable horizon. But the galaxy clusters that were pulled toward it kept moving. Momentum. They are still drifting in that direction today, billions of years later. This hypothesis has a problem. If something that massive exists just beyond the edge, then the universe is not homogeneous. It is lumpy. And if it is lumpy, cosmic inflation does not work the way we think it does. Inflation was proposed specifically to smooth out the universe, to make it homogeneous. But if the universe is not homogeneous on scales larger than we can see, then why did inflation happen? What caused it? The theory starts to unravel. Option 3. The cosmological principle is wrong. The universe is not isotropic. We are in a special location. Or the universe has large-scale structure we do not understand. This is the most radical option. Because if the cosmological principle is wrong, then the entire framework of modern cosmology needs to be revised. The Friedmann equations, which describe the expansion of the universe, assume isotropy. Dark energy calculations assume isotropy. The age of the universe, the Hubble constant, the density of matter, all of it is based on isotropy. If the universe has a preferred direction, all of those calculations are wrong. Not slightly wrong, fundamentally wrong. And there is a fourth option, one that nobody likes to talk about. We are measuring something wrong. The instruments are fine, the data is real, but our interpretation is flawed. Maybe the CMB anomalies are caused by something local, dust in the Milky Way, magnetic fields, foreground contamination. The Planck team spent years trying to rule out these effects. They modelled the galactic foreground, they filtered it out, and the anomalies remained. But maybe there is something we are missing, some systematic error we have not accounted for. It is possible. But after 2 decades of analysis, with multiple independent observatories confirming the same features, systematic error becomes less likely. So where does that leave us? In 2024, a team at the Max Planck Institute ran a statistical analysis. They combined data from WMAP, Planck, and ground-based CMB observatories. They looked at all the anomalies, the axis of evil, the cold spot, the hemispherical asymmetry, the low quadrupole, and they calculated the combined probability. The odds that all of these anomalies could exist simultaneously by random chance. The number they got was less than 1 in 10,000. Those are not good odds. Either we are extraordinarily unlucky, or something about our model of the universe is incomplete. And here is what keeps me up at night. These anomalies are at the edge, the very edge of the observable universe. The CMB is the oldest light we can see. It formed 380,000 years after the Big Bang. Before that, the universe was opaque, a hot plasma. Light could not travel through it, so the CMB is a wall, a boundary. We cannot see past it. And that boundary has structure, it has direction, it has a symmetry, which means the universe beyond that boundary, the universe we cannot see, might be very different from what we assume. It might not be uniform, it might not be isotropic, it might have massive structures, voids, concentrations of matter that we will never observe. And if that is true, then we are not just missing a piece of the puzzle, we are missing half the puzzle. The James Webb Space Telescope is now observing the early universe in unprecedented detail. It is finding galaxies that formed earlier than our models predict. Galaxies that are more massive than they should be. Structures that assembled faster than gravity should allow. And every time we push our instruments further, we find more things that do not fit. More anomalies, more precision that breaks the models. Maybe the universe is trying to tell us something. Maybe the edge is not just a horizon. Maybe it is a boundary, a transition between the universe we understand and the universe we do not. Make sure you are subscribed, because as new data comes in from James Webb, from upcoming CMB missions, we're going to break it down. We're going to follow the anomalies, ask the questions no one else is asking. If you love this kind of deep dive into the mysteries the data keeps revealing, hit that like button. Share this with someone who thinks they understand cosmology, because after watching this they might not be so sure. The edge of the universe has a direction, and we are only beginning to understand what that means.